a discussion of the results of the two-dimensional airfoil testing lab at the Pennsylvania State University. In this presentation, we're going to cover the lab introduction and the procedure for the experiment. We're going to discuss the results, and we're going to give a few conclusions that we've drawn. In terms of goals for this lab, we wanted to determine a relationship between the coefficients of lift, drag, and angle of attack, as well as compare these results to published data. We also wanted to explore stall properties of a specific airfoil at a specific wind speed. And we also wanted to look at how the data we found explains boundary layer separation, turbulence, and viscosity. This is a diagram of the NREL S-805 airfoil that we're going to be using in this experiment. Next up, Michael is going to discuss the procedure of the experiment.
All right, for this lab, there were two parts, and they were, the first part was two simultaneous measurements. One was with the manometer that was reading the pressure from the pressure taps of the wing, and the second was a wake survey using the hot wire anemometer. In the second part of the lab, we measured the stall angles of the wind at 50% to determine where it stalled at and then where the flow reattached. For the manometer, we first recorded the lab environment conditions, which were the temperature and the pressure in the lab. Next, using the lab Excel sheet that was provided, we plug in the environment values to get the transducer voltage that we need to get in the wind tunnel for the required Reynolds number of 700,000. Next, we rotate the wing segment to the desired angle of attack that our section was assigned. With the assistance of the TA, we rotated the manometer bank to get the best resolution of the tubes, and we powered the wind tunnel up to the transducer voltage that was given by the Excel sheet. As the flow was going, we recorded the levels in the manometer tube, and then we powered down the wind tunnel to change the angle of attack, and then recheck the lab environment conditions as they could change during the experiment. We repeated all the steps discussed for the new angle of attack. Next, Grant will discuss the rest of the procedure and some of the results.
So as we were altering the angle attack and collecting the pressure data, we had a hot wire that would measure the velocity of the flow behind the airfoil. It would go from 24 inches from the bottom of the airfoil down to 6 inches, and it would collect data every 0.125 inches, and this was done with the transverse mechanism you can see in the picture there. And for the second part of the lab, we tried to observe the stall of the airfoil, and by doing that, we took the airfoil and increased the angle of attack until there was a sharp pressure drop, and we recorded that angle, and then afterwards we decreased the angle of attack until there was a reattachment. We used the same manometer for this experiment. And then we went and calculated CL versus alpha. We did this by using the pressure we calculated from each of the points seen earlier in the presentation. And as you can see here, our data follows pretty similarly to the experimental. As you can see that our zero angle of attack is pretty much the same, and it follows the same trend as you would expect in an airfoil that looks like this. Next, we are going to have Andrew talk about the velocity profiles.
So when getting the velocity profiles of two angles, we have -12 degrees and +7 degrees. For the angle of attack -12 degrees, notice how the wake is actually a lot wider than what it is with +7. With +7, it's actually sharper, and this is actually what we expected. With the smaller angle of attack, regardless of positive or negative, we're going to expect a sharper and shorter wake. And other labs groups actually experience this whenever you had +3 angle of attack or -2. So what we did was we set an arbitrary point at around this height for V1 and below the wake for V2, being 73.5 459 feet per second, and V2 being 75.02 feet per second, respectively. And we average these two out to get V naught. Now V naught is going to be used as our constant V value to calculate CD later. For the 7-degree velocity profile, our V1 was 71.777 feet per second, and our V2, below the wake, is 72.235 feet per second, giving us a V naught of around 72 feet per second. This is used in our CD equation, which we then use to calculate CD versus CL. And notice that the trend is still there. The trend in behavior actually resembles the true value. Although there is error that John will discuss later, generally the trend and behavior still follows. Up next, John will be discussing the CD versus angle of attack graph and the conclusion.
Okay, so the last part of this lab was an optional plot of coefficient of sectional drag versus angle of attack alpha. As you can see, the rough bucket shape, as was expected from airfoil theory in general and from other labs in this course, was there. There are some bumps, but the rough bucket shape is still there. In conclusion, thin airfoil theory has been verified by our measurements. We also demonstrated the effects of viscous flow over an airfoil. And all the effects that we measured in our lab would not have been present at all if the flow were perfectly implicit. When it comes to lift, the measured zero lift, the zero lift angle of attack was the same as the published data. The maximum coefficient of lift was about the same, and the trend was the same. When it came to drag, the rough drag trends were the same as published data, as were the maximum and minimum, about the same. And when it came to stall, the angle of reattached flow was smaller than the initial angle of detached flow. We believe that this was due to the fact that in order for flow to reattach, a turbulent boundary layer must be transitioned. And in order for that to happen, a shallower angle of attack has to be reached to give time for the flow to transition from laminar to turbulent. In all, we believe that the sources of error that were observed in our data mostly came from unintended or unexpected turbulent effects, vibrations in the airfoil, and potentially boundary layer development across the walls of the wind tunnel.